discovered Cas280 peptide. And as you can see, it's bigger, and it's got the same stability as the recent. And this is biologically active C-drug. So we're going to talk today about four aspects: GRP in the normal brain, where it functions as a modulator; GRP in cancer cells, where it functions as an oxidative factor. We'll be discussing how GRP receptors regulate tyrosine phosphorylation receptor tyrosine kinases. And finally, we'll be localizing GRP receptors to ascertain glioblastoma tumors. So the GRP receptor is discretely distributed in brain neurons, and it's present in the lateral hypothalamus, where it functions as an anxiety agent. It's present in the medial preoptic area, where it causes hypothermia. It's present in the supraplasmatic nucleus, where it alters circadian rhythms. And then you could say it's also present in the olfactory tubercle. The main function of these in the brain is curatus. So when you inject poppies into the rat there goes hyperactivity, and GRP is associated with this receptive signals require repetitive firing to excite for increased synaptic GRP neurons. And you see that GRP receptors, as well as peptides, are localized in the dorsal spine. In contrast, the substance B receptor, which is associated with pain, is present in the dorsal, ventral, and lateral spinal. So in the brain, obviously, GRP is secreted from brain neurons, and it is synaptic receptors, altering behavior. But in the cancer cells, it functions as a monocyte growth, whereby it's made in the cancer cells, secreted, and binds to receptors on the cell surface to stimulate growth. This was first illustrated in small cell lung cancer. This kills approximately 30,000 US patients annually in the US. And it's a small cell lung cancer is a neuroendocrine tumor that's responsive to chemoradiation therapy, but relapse frequently occurs. Median survival is 1 year. And here you see that the small cell lung cancer cells have dense core neurosecretory granules. These granules contain GRP. We also see lots of neurotensin in them. And there's neural enzymes, the carboxylates, neuron-specific enolase, and then the transmitters are also present. So there's 3 types of G-protein-coupled receptors for bodies like peptides. The one receptor binds neuroweak B with high affinity, and neuroweak B has 7 of the same 10 C-terminal amino acids as to recent. The B2 receptor binds GRP and ribosin with high affinity, and BRS3 is an orphan receptor. However, Dr. Coy of Tulane University synthesized agonists, tyrosine 6, LA11, B13, northern 14, ribosin 614, and this PA1 functions as a universal agonist, stimulating BB1 receptors, BB2 receptors, and BRS3. There's about 50% sequence homology between the 3 types of obese receptors. There are about 190 amino acids inside, and contain 7 transmembrane domains. The obesity receptors are not only present in small cell lung cancer cells, they're also present in non-small cells. And you see that BA1, ribosin, and GRP bind with high affinity to the cancer cell. Neuroweak B binds with the corners and maybe to lower affinity. And PD-176-252 was synthesized by using colleague of the United. And this is actually a tripeptide with tryptophan in the middle And on the upper right, we have a benzene ring with a nitrate. And at the bottom right, we have a pyridine ring with an artery. For the two receptors, the PD-176-252 has an oxygen. For the one receptors, 168-368 has a series. And we collaborated with Dr. Leopoldo of Italy, besides a series of PD-176-252 analog that we analyzed. And at the top, you see that the benzyl nitrate binds to a cysteine 196, and the tryptophan in the middle binds to a serine 179, and the pyridine epoxy binds by affinity to interacts with an arginine 287, tyrosine 284. Each of these amino acids are as an extracellular domains of the BD2 receptors. And the BD2 receptor causes phosphatidylinositol turnover after it interacts with BD2. You see that obesity to the non-small cell lung cancer, calcium goes up within seconds. At PD-176-352, and those dependent matter blocks the receptor, so that when you add obesity, there's no increase in cytosolic calcium. So Kromer and colleagues in Germany first found that peptides can cause tyrosine phosphorylation of receptor tyrosine kinase. And this slide shows that using small cell lung cancer cells, the BA1 increases the tyrosine phosphorylation fourfold, and this is inhibited in a dose-dependent manner by the PD-176-252. Also, the ERK is increased about twofold, and this increase is reversed by the PD-176-252. And ERK is associated with increased cancer site growth. So there could be receptors in the family of EGF receptor binds EGF and TGF-alpha with high affinity. Then there's a single transmembrane domain, and then on the cytosolic side, there's a tyrosine kinase domain, which can cause tyrosine phosphorylation proteins. In contrast, the HER2 receptor, or HER2, has no known ligand binding, but it can be tyrosine phosphorylated. And primarily the way this is done is by forming heterodimers between the EGF receptor and HER2. Also, HER2 can form heterodimers with HER3. HER3 is activated by uregulin, binds with high affinity, but HER3 has weak tyrosine kinase activity. And HER3, however, forms heterodimers with HER2. This leads to tyrosine phosphorylation, or it can form heterodimers with EGF receptor. This leads to tyrosine phosphorylation. So for the EGF receptor, you see it's large, 186 amino acids. It's got 4 extracellular domains. Domain 1 and 3 are involved in ligand binding. For domain 2 is essential for heterodimers. And we see that for the EGF receptor, there's a variant 3, which lacks over 260 amino acids in the extracellular domain. Hence, it doesn't coordinate EGF with high affinity. And secondly, it can't really form heterodimers because of the lack of the domain 2. I think one of the EGF receptors amplified in 57% of patients. EGF receptor variant 3 is present in 12% of patients. For non-small cell lung cancer, the EGF receptors are mutated, and the patients with mutated EGF receptor highly responsive to inhibitive or tyrosine kinase inhibitors. In contrast, the glioblastoma patients are not sensitive to inhibitive or inhibitive, probably because of the ability to cross the HER3 can also be tyrosine phosphorylated by things like peptides. And we see that we add 100 nanomolar all of a sudden we get phosphorylated EGF receptor, HER2, HER3 in 3 minutes. Subsequently, downstream, we get phosphorylation of the HER and the AKT. The HER is essential for cancer cellular growth, phosphorylate AKT, cancer cellular survival. HER3 is also activated by Regulin 1. And when we activate HER3 with Regulin 1, it then forms heterodimers with the EGF receptor HER2, causing them to be phosphorylated. And Regulin 1 addition to the non-small cell lung cancer cells also increases HER phosphorylation and AKT phosphorylation. The main thing that the obesity-like peptides do is stimulate growth. Here you see the colony forming assay using C6 cells, which have neurobeat B receptor. Then when we add neurobeat B size, the number of colonies increases. We add an antagonist, the number of colonies increases. This is a cartoon illustrating the transactivation phenomena. The G protein coupled receptor causes PI turnover, rapidly increasing cytosolic calcium and activation of protein type C. And then after about a minute, we have GRP in the cells. EGF alpha is increased in the cytosol. Normally it's present in the membrane. It's an inactive precursor. And for the TGF alpha to be released, we have to have a slow start and activated atom or B. And the TGF alpha will then bind to the TGF receptor, which is called heterodimeric HER2, or the heterodimeric HER3, causing phosphorylation of the receptor tyrosine kinases. And downstream, we see we get HER phosphorylation, AKT phosphorylation, which leads to cancer cellular growth and increased survival. The remarkable thing about this process is how rapid it is. We had obesity of lung cancer cells, we get phosphorylated EGF receptor, and then after several minutes later, we see phosphorylated EGF. So the glioblastoma cells, the GRP receptors are present in gliomas, but not glial cells. GRP stimulates the growth of the cells, and the GRP receptor inhibits proliferation in vitro. And then in vivo, the GRP receptor antagonist becomes on decrease tumor growth. So a ligand was then made to image the glioblastoma, utilizing the GRP receptors. So we have the obesity-like peptide, the C-terminal, the 7-G. We have a linker, HCA, and there's nona that intercalates a gallium-68. This is that for imaging. And on the left, you see a CT scan with that sort of like alpha tumors. This is a photobiopsy glucose scan, and you can see tumors, but there's lots of other things that light up as well. And then when you use the probe for the GRP receptor, you get a discrete tumor with a well-defined margin. And these are 3 different patients giving the same. And then if you biopsy the sample and you stain it, you see GRP receptor. So then Zane and colleagues